Hello, my name is Scott Mesjin, and welcome to Week 8's second explainer video on the black hole thermodynamics. So this is the main page for the topic. I've, gotten my own, so we'll just work off of that. The first task in 2.1 is to find the signs of the change in temperature, and then see the specific heat. Here we have our little drawing of the black hole. Black hole has mass of m, its radius is rs, and we're assuming that we throw some mass into the black hole, and we want to see how the temperature changes of the black hole to find its specific heat and change in temperature. So we'll start with Q equals mcat, an equation we should know, and then obviously we know that the mass of the black hole is equal to the mass of the black hole. That's kind of that makes sense. But then we'll add this equation to it, Q equals mc squared, and we derive that from Einstein's equation, E equals mc squared. But we're just saying Q here because we're specifically talking about heat. Um, so all the energy is going into heat instead of whatever else it could be. So here we've added those two equations together. Okay, cool. We'll use that later. So now we want to find specifically the sign of delta T. We know that delta T is the final temperature minus the initial temperature. And we get this T equals this whole thing. This is an equation that's given to us in the problem, so we'll go ahead and use that. And initially we notice that the mass is m, but after we add um, the rock, I guess, the mass will be a little bit greater. It'll be the mass plus the energy of the mass of the black hole plus the energy of the rock. So then we know that since the denominator of the final will be greater um, than the initial, we know that this final value will actually be less. So since the final is less than the initial, we know that final minus initial is a negative number. So therefore, the change in temperature is negative. When we look again at Q equals mcat, we know that Q is positive, the energy. The mass is positive. We don't know what the specific heat is yet, and we know the temperature is negative. So therefore, C must be negative for these signs to work out because positive must be equal to positive times a negative to be equal to a positive. All right. For the next part, entropy, our next task is to solve this using an integral basically. And if we recall, this is given to us in the document that the integral of x is just equal to half x squared plus c, but we don't really care about that. And then here we will call this other equation that we used in the previous part up here. And we will be substituting this in for BH when only the mass is plugged in, not m plus mc squared. So let's go ahead and do that. Basically what happens is since TBH is on the bottom, these will be flipped. So whatever is in the denominator here will be in the numerator here, and vice versa. And now we can do some integral magic, and basically what happens is our only real x here is the m, so m gets squared, and we multiply this by half, so that 8 that we had before becomes a 4. So it goes to 8 to 4 because it's divided by 2. So now there's a tricky part. You have to substitute in these two equations they give us, but you have to substitute both of them in twice. So that may not have been immediately obvious, but that is indeed how you get from here to here. And then once you're there, notice that you have this pi r squared s. So that shows that the area of the black hole is what contributes to entropy, and that is the whole revelation of this problem. So yeah, thank you for listening, and I hope you found that informative. Thank you.